Problem number 7. This is kind of a classic optimization problem. What's going on here is that we have a piece of paper or cardboard or whatever that is 16 inches by 21 inches here. And then we cut out corners here from each of the 4 corners, cut out little squares from each of the 4 corners here. And all 4 of these squares are going to have the same dimensions here. So I'm going to call the dimension here x. And the idea is that you fold on these dotted lines that I'm drawing right here, and you fold this up, fold, and you end up with some kind of little box here. Okay, not my best box ever, but you get the picture for what's going on. Okay, so our goal is that we want to maximize. The goal is that we want to maximize the volume of this box here. Okay, what are the dimensions? So we know that the volume of this box is going to be base times width times height kind of thing here. So we need to fill in all of that in terms of x. So the height of the box, is going to be the height of the flap that we fold up, and that's going to be x. How about this side and this side? So this side will correspond to this distance here. Well, this whole thing is 16. Subtract off x, subtract off x. This is 16 minus 2x. Okay. How about the other side here? Well, this whole thing is 21. Subtract x, subtract x. This distance right here is 21 minus 2x. So the volume is going to be v of x is going to be this times this times this. X times 16 minus 2x times 21 minus 2x. So our goal is that we want to maximize volume. We want to make this as big as possible. We want to, but we should be thinking, of course, about what are the constraints here. It's not meaningful to just say make this the biggest possible, but make this biggest possible subject to what constraints are occurring here. And so let's see here. The first thing is that the smallest x can be is 0. X can't be negative. We can't cut out a negative amount of material from here. And you could even argue that we shouldn't be allowed to set x is equal to 0, because that would be cutting nothing here. Cutting nothing would correspond to a box that has no height and we have volume 0. It's easiest to just kind of say that x can be 0, and that's the degenerate solution that will give us a minimum volume of 0. What's the biggest x can be here? Well, if we make x too big, then we cut out the entire side here, and there's nothing left. So how big would be too big? We want 16 minus 2x to be non-negative, which means x can be at most 8. If x is bigger than 8, then the squares that we're cutting out are overlapping. There's nothing left to the side here. Note that this side also gives us x can be at most 10.5. By a similar argument, 10.5 is bigger than 8. We go for the tighter bound here. So our goal is that we want to maximize the volume here on this interval. Of course, v of 0 and v of 8 are 0 here. So those are the endpoints. Now we just need to try to see what critical points are at the interior of this interval. So v prime of x, so we take the derivative here. This will be by the product rule. It will be x times, I'm going to kind of group all of those terms together, for product rule purposes. So it's x times the derivative of this, which is going to be 16 minus 2x, times the derivative of this is negative 2x, plus 21 minus 2x times the derivative of this is negative 2. Oops, that shouldn't have been a negative 2x. That should have just been a negative 2. Plus 16 minus 2x. So now we're doing this times the derivative of this, which is just going to be 16 minus 2x times 21 minus 2x times 1. Okay, so we want to take this and set this equal to 0 and solve this equation here. So the first step that we would do is, I don't really think there's an easier way to do it than this. Just kind of expand out all of this multiplication here, do lots of algebra. In the interest of time, I'm just going to kind of skip through lots of steps here. So at the end of the day, you should end up with 12x squared minus 148x plus 336 is equal to 0. So you expand this out, this is what you should be left with. Okay, we want to solve this equation here. One easy thing is that all of these terms here are divisible by 4. So let's divide by 4 on both sides. And so we'd have 3x squared minus 37x plus 84 is equal to 0. And now this is a quadratic equation. This is also a quadratic equation. This is a little bit simpler one. Let's use the quadratic formula here to solve this. So x is equal to negative b, 37, plus or minus square root of b squared, negative 37 squared, minus 4 times a times c. All of this over 2 times a, 2 times 3. And if you crunch this out, you end up with 37 plus or minus 19 all over 6. Okay, so this has two solutions. X is going to equal, if we have 37 plus 19 over 6, 37 plus 19 would be 54 over 6 is 9. And we do 37 minus 19, this is 56 over 9, which is 9 plus 1/3 there. If we do 37 minus 19, we get 18 over 6, which is 3. Okay, so how do these play out around here? Well, 9 1/3, that's too big. That's too big. That's outside of our interval that we care about. So let's cross this out. X is equal to 3. X is equal to 3 is our only critical point here that falls in the 0 to 8 interval. Okay, so what is v of 3 equal to? Let's plug in 3 up here. 3 times 16 minus 2 times 3 is 10. 21 minus 2 times 3 is 15 here. And so this is 450, and that's going to be our maximum. And so, we get the maximum possible volume here if we cut out 3 by 3 squares here.